at Boston Atomics, we tried to do an estimate of what it would take, what's the total capital required to get the first of a kind version of our reactor through detailed design and licensing. And we sort of always had this number, even from the very beginning, that was something on the order of $1 billion. And that was based on historical reactor designs done in the US and abroad, whether through national labs or through private companies. And late in 2023, we started comparing that number to other multidisciplinary design problems, right? So one interesting way to look at this is to say, well, what was the cost to design and engineer the Model 3 from Tesla? And it's, about $1 billion in design and engineering. And this is an electric car, right? It's less parts than an internal combustion engine car. And that's a lot of money for just the design and engineering. Now, there's a lot of prototyping along the way, but that's what it was. And you can also look at how much DOE money was appropriated to Westinghouse to do the design of the AP1000. And if you sum up the appropriations over 15 or 20 years, you get something close to $1.5 billion.
Welcome back to Decouple. Today I'm joined by Robbie Stewart and Enrique Velez-Lopez. Robbie and Enrique are both academics, are studying at MIT, co-founders of Boston Atomics. And today I'm really excited to chat with them to gain a realistic picture of some of the financial and R&D challenges to bringing advanced nuclear to a state of commercial readiness, as well as some of their other activities at MIT, including their nuclear plant cost modeling tool and tons of other insights they've got from their backgrounds in the sector and their studies. So great to have some nuclear academics on the show. It's going to make it real spicy, I'm sure. Welcome, guys.
Welcome.
Great to be here.
Yeah, great to be here. Just a small note here. I don't consider myself an academic, in fact, because I went to university as every other person in the nuclear industry doing engineering. I did master's, didn't do PhD, and most of my life has been in industry experience more than working inside. MIT university and so on. But
it is an interesting one because Enrique, notably, in lieu of a PhD, did 4 master's degrees in civil, mechanical, nuclear, and numerical methods. So he has his time in academia, but I will accept his label of himself as an applied engineer.
Yeah, true. I mean, that technically makes me also sort of an academic, to some extent. I accept that, but I like to think about myself, perhaps wrongly, as somebody in both worlds.
Yeah. Do the crime, serve the time, man. You've been in there a long time. Let's just get a little bit more of your individual backgrounds. You give us a little sneak picture there. Enrique, do you want to kind of fluff it out a little bit more so we have a sense of
Sure, yeah. So Enrique Velez, I worked for a number of years in the nuclear industry in Europe before coming to the US. There I did my undergrad and master's in electromechanical engineering. I was working first doing post-Fukushima retrofits as a structural mechanics specialist in the Spanish nuclear fleet. Then went to Belgium to work in an advanced reactor project for 3 years. In that journey, I realized that one of the hardest part, especially in advanced reactor projects, the more advanced the reactor is, the more difficult it is multidisciplinary integration. Essentially, making people from different disciplines speak to one another, reach agreements, and collaborate towards the design to make sense as much as possible. Many times we see that some discipline is more represented in a team and outweighs the other, and that may make happy the members of that team because they're mostly specialists in that discipline, but that doesn't make the design better or easier toward the future. So I decided to pursue education in many different disciplines that I consider very important for nuclear. That's why I came to MIT for doing a master's in civil engineering and a master's in nuclear engineering. In that journey, we invented the MIDE reactor. We patented it. We created Boston Atomics, and this has been going on for the last 5 years approximately. Robbie will speak more about the history of Boston Atomics, but this is essentially my
your trajectory, the embodiment of systems analysis, of multidisciplinary approaches, which seems really important because certainly, at least as a non-academic, as an anthropologist of nuclear, You see lots of PowerPoints, lots of, the focus is really on, hey, this cool, shiny bit of technology, the NSSS, and not a ton of focus on civil works. And I think that's going to be a theme of our conversations today. Before we get there, Robbie, give us your back history. I know you worked on jet turbines a lot.
So I
working. Yeah.
So I started in mechanical engineer, undergrad and master's, UT Austin, and moved up to Schenectady, New York, and worked for GE's Global Research Center. So I worked for their research center for 4 or 5 years, and most of my time were contracts with the GE's aviation business, what's now called GE Aerospace. I did a little bit of work along the way with GE Power, which was a land-based gas turbine industry, but all the things I did were turbine related. A lot of stuff in testing components for the hot gas path. So this is like the turbine inlet where things are really hot and high pressure. And then I did a lot of work in fleet modeling. So the end of my time there was how to track how different airlines were operating their engines and how that would project what their maintenance requirements would be. But I wanted to spend the rest of my career, I realized I was still a young engineer and I had a lot of time to put forward towards climate tech. And I was trying to figure out where does my skill set and expertise match there. And so I went to MIT to do my PhD in nuclear science and engineering. And it doesn't take long once you're in the nuclear world to realize that the primary challenges facing the industry and facing more deployments of technology, at least in the West, are cost and construction risk. And so I focused my PhD on that area. So I built a cost modeling tool to sort of evaluate, can small modular reactors overcome the economy of scale that they lose by reducing size through things like being a lower financial risk project, more extensive modularization, and a number of other factors. Built a tool to evaluate that, and that became my PhD thesis. And then sort of as Enrique alluded to, we met as students in our first year working on our project, recommending new nuclear technology to Japan. And that was sort of cemented the reactor concept at the core of Boston Atomics. And we can get into that maybe in a second.
Yeah, for sure. I'm definitely interested in the nuclear plant cost modeling tool as a way to, I think, kind of better inform the discourse again when trying to make decisions, when trying to design reactors to optimize, again, the non-sexy things, the kind of labor needs and cost of civil work. So is that like a novel tool? I mean, there must be previous attempts at this. What's new about your guys' approach?
So this tool was the first, I think, to try to do several different reactor concepts. There had been a number of academic papers in the last 15, 20 years on estimating cost of reactors. So a lot of conceptual academic reactors designed in different parts of the US and Europe, there was always a cost model behind them, right, justifying continuing to work on that technology. But it was very rare that you would see the model underlying that concept applied to other reactors. And at the same time, you see a lot of cost targets from reactor developers, right? People saying, our reactor is going to be $1,000 a kilowatt, $2,000 a kilowatt, whatever sort of the number was. And it was hard to know what the basis underlying that assumption was. And so what we wanted to build at MIT was a tool that could, across all light water reactor concepts at the time, we've since expanded it to some others, but across different reactor technologies, have the same set of assumptions, start from the same bases of what your concrete is going to cost, how much labor it's going to take to install that concrete and rebar and those components, and evolve that forward into a cost rollup. At the same time, you wanted to estimate like how much modularization was going to move your site work to a factory. And that's sort of the promise of SMRs and even large modular reactors, is that you're going to move a lot of that site work to the factory. And the question was, how much of that can you do? And even if you do a significant portion of that, how much site work are you left with, right? If I move all of my nuclear steam supply work, labor to a factory, and I don't have to do any labor for my nuclear steam supply system, does that dramatically reduce the total number of labor hours on site? Or is there still so much other concrete, so many other systems, so much other rebar that you end up with a significant on-site construction project anyway? And so that was the goal of that tool. And And it's a publicly accessible tool. Anyone can go download this tool on GitHub. MIT maintains a copy of it through the Nuclear Science and Engineering Department.
So what sounds different there is you have probably more sort of proprietary models used by reactor vendors to justify their cost estimates. And there's obviously a bit of a moral hazard there, or some degree of self-interest, maybe to tweak the numbers a little bit. Is what's different here. This is kind of an academic, publicly accessible tool with clear parameters of what's sort of spitting out the numbers at the end that you can apply more broadly.
Yeah, exactly. So you can come into the tool and instead of telling me what your pressure vessel costs, you tell me how much it weighs. Instead of telling me how much your reactor building costs, you tell me how big it is, and then I'm going to estimate the amount of concrete, the amount of rework required, the complexity of installing that concrete. And because it's, I think, easy to sort of say, if we build this nuclear project with costs comparable to a chemical engineering project, then maybe your reactor looks like it's going to be very cheap or very competitive. But the problem is, in reality, that's not, the concrete for nuclear projects is different. The construction methods you're doing, the QA, QC, the traceability on all of your materials is different. And so you have to start from a basis of nuclear costs to do your estimate of your plant. And that's, I think, still somewhat of a novel.
Well, let's get into that a little bit later, maybe as we talk about best practices moving forward, large modular, small modular. But I'm interested in hearing your guys' personal story with Boston Atomics, with MITRE, as a way to illustrate, I think, what are often the kind of underestimated challenges of bringing advanced, or what I've called in the past, failed to advanced nuclear reactor concepts to the fore. I mean, we have things like the, what's it called again? The Cooperative Power Reactor Demonstration Program that Nick Turan has went into in the past. A lot of these concepts are indeed Back to the Future reactors, have been attempted, but were just operationally not so good. So yeah, curious about your endeavors there, and particularly just a kind of mature, realistic sense of what it takes and what kind of capital can meet that challenge. There's no doubt that we need some of the promises that these technologies offer beyond just conventional light water in terms of process heat and other applications, but I think the challenges are often underestimated. So yeah, interested in your guys' path there, however you want to.
Yeah, absolutely. So I will tell our technology story and then some of our commercial story as well. And I will tell our technology story because I think it's helpful to see where we think innovation needs to happen in nuclear, and that the focus of innovation sort of in the idea of constructability or value engineering and multidisciplinary systems integration, which is a much harder, more nuanced problem to solve than like optimizing your core fuel or something along those lines. And so we started, like we mentioned, we were working on a project recommending nuclear technology to Japan if they were interested in sort of re-engaging in new nuclear in the 2030s. And this project recommended 3 technologies. It recommended small modular boiling water reactors, high temperature gas reactors for a lot of the industrial processes that happen in Japan, and the last were microreactors for some of the island communities. And at the time, this is like 2018, 2019, the most advanced HTGR was the Framatome SC HTGR. And this is a very large high temperature gas reactor. It is 225 megawatts electric. The vessel is about the size of the ABWR or ESBWR vessel. So it's like 1,000-ton vessel. So it's three times larger than a PWR reactor pressure vessel, but producing a fifth of the total power. So this is a massive vessel in an extraordinarily tall building. When we did an estimate of the volume of the seismic Class 1 safety grid building volume, it was like half the size of the Empire State Building for this reactor. And
so this is a reactor that's never been built. This is a concept? Or? Okay.
And we were recommending this technology, at least the faculty group in this research project were recommending this technology as part of where Japan should consider going. And that's, there wasn't another HTGR at the time that was as developed to point to. And Enrique, as the civil engineering master student at the time, coming to work on the project and with experience in mechanical and civil structures at both existing light water reactors and advanced reactors, looked at this and said, if we're having trouble in Flamanville and trouble in Vogel and trouble at OL3, why are we going to go make everything so much bigger and more complicated and more difficult to install and more difficult to construct? And so he actually wrote this memo this is, I think, in 2019, that if someone goes to build this reactor, it's going to be $20,000 to $30,000 per kilowatt. And I, I'm like 9 months into my nuclear world, coming from gas reactors, still trying to understand everything that's going on. Very naively, I'm like, that's crazy. There's no way it could ever be that much. This technology is great. The U.S. has invested so much in trying to get the fuel ready and evolve all the components through different national lab programs. We've been working on this for like 40 or 50 years. It's got to be a better technology than that. And it was actually in the course of those conversations that we had sort of the breakthrough that became the Center of Boston Atomics, where we said, okay, if the problem is that the height of a structure determines how fast you can build it, how do you make it shallow? Well, you have to turn the whole system horizontally and lay your reactor pressure vessel on its side. And so that was what the first sort of key innovation at Boston Atomics was. Like, let's, instead of going from a vertical vessel that makes your structure 80 to 100 meters tall, you have to lay it all flat, and then you can go to like a 15-meter tall structure.
We love horizontal reactor vessels.
You know what?
I'm not sure it really reduces the height of our reactors that much because we have these big steam generators above.
That's also a very interesting conversation on how to reduce the height of candles and make them more constructible and cheaper. Like, we have some ideas, but probably for another day.
You can adopt the Russian. Russia has horizontal steam generators, so you could do a little.
I've heard that.
And that makes their reactor buildings shorter, actually. If you look at the Vivers, they have shorter reactor buildings. And so this is generally, I think, assumed in construction. Like, if you're building the line Enrique would tell at the beginning was, if you're building in Kansas, you don't build a skyscraper. So like you want to build something flat. And no offense to my friends in Kansas. And there's just a lot of land.
And sorry, just for people that, it's just wide, expansive.
Exactly.
You can sprawl.
Exactly.
Horizontally. Okay. You don't need to build pencil towers like
exactly. And so the other innovation we did was Enrique looked at the cross vessel. So in a HTGR, you kind of got this like vertical reactor pressure vessel, and it's like laterally and vertically offset from a steam generator. And there's a vessel between those two, and installing that vessel, qualifying that vessel because of the types of loads it sees in different accident scenarios is actually really difficult. So Enrique's like, well, can we get rid of this vessel? And can we integrate these two and sort of into a single long flanged structure? And that became the nexus, sort of the beginning of Boston Atomics technology. And we had to go and convince our faculty advisors at the time, because we were students. This is like 2019, we're students, that this was a good idea. And about 6 months later, the DOE announced the Advanced Reactor Demonstration Program. So this was a program to develop and deploy demonstration advanced reactors. But there was a part of that program that was on sort of far out 20-year concepts. And so we convinced our faculty advisors to put in a proposal. Professor Karush Shervin did a phenomenal job assembling a consortium of folks from MIT, University of Michigan, University of Buffalo, Argonne National Lab, and NPR Associates. So he put together this great consortium. And starting in 2021, we spent 3 years doing the sort of initial technology de-risking of the Boston Atomics MITRE in that program.
A few notes here. The first memo that I wrote on the SE HTGR cost, of course, was an extremely rough calculation and was just aiming at the order of magnitude. So I came up with $20,000 to $30,000 per kilowatt installed, but we acknowledge that it could be more than that or less than that. It could be 10 or 15. I just wanted to show that the projections that we were seeing back in the time for HTGRs that could be the holy grail and be extremely cheap, much cheaper than light water reactors, were not based on actual engineering. They were based only on hopes that have been extended over all the industry, but that wasn't the truth. When you would bring that type of design to a large engineering team with people from every discipline, each of them imposing their own conditions, and each of them making the wall a bit thicker, the building a bit taller, this pipe a bit longer, more valves here, more redundancy here, what would happen is that you would get to a cost that nobody could guarantee that would be lower than this for a light water reactor. In fact, it would probably be higher. So that was the whole point of the memo, not actually coming up with a realistic or credible cost estimation. The other thing that I wanted to mention is that when we started working on MITRE, and also this memo was totally out of the project time. out of the time that MIT was funding from us to do the technology selection for Japan. So from the very beginning, we started doing this in our free time during weekends and in spare hours. And we brought it from here to try to convince the faculty to put this proposal for DOE to participate in the Advanced Reactor Demonstration Project. But before that, we submitted a provisional license. There's a story also about how we submitted the provisional license through MIT. Today the patent is owned by Boston Atomics, and that was the story of how the company was created and the project started.
Yeah, it's interesting. I've toured, I think, a few LWRs, a lot of CANDOs, and I actually got to tour Hunterston B, which is one of the HTGRs, the advanced gas reactors in Scotland, when we were up at the climate conference in Glasgow. And it was just this magnificent building. It was so tall. I think it was at least 5-6 stories, but the fueling machine was another 3 stories because it had these really long fuel elements, and refueling a gas reactor was under the water interface and all that shielding. And so the refueling machine was just bonkers in terms of the shielding within this big tube that they'd swap out the elements with. It seems like the nuclear industry, I think it's partially a product of having such siloed expertise, really, really smart people, but working in silos, that there's the potential to embrace a false paradigm, which is something you might need more of a kind of interdisciplinary systems and kind of level analysis to pick up on and catch. And to me, that seems to be what's driving a lot of the issues that you guys are finding, I think, with your cost estimation tool of, okay, the whole paradigm and idea here is to shift work into the productive factory, get it off the unproductive construction site, but that's not occurring. That seems to be something you're identifying with the high temperature gas reactor being recommended to Japan and trying to fix in your own model by making it horizontal. How does it look when you sort of put your own reactor through the gauntlet of your cost estimation tool?
Yeah. This is a really interesting question because I love that the AGR is the perfect example here because, while they were quote standardized, every AGR is different. AGR engineers will tell you that they're like Swiss watches. These are like remarkably complex machines that to operate and maintain and to construct they were. And the refueling machine is the perfect example for where I want to go with this. It adds so much building volume because you have to be able to extract all the way from the base of the core. This, I think it's like a 12-meter long fuel assembly that you've got to pull up. And so you need all that space up above to pull the fuel assembly into. And when we did the first cost estimate of MITRE, we didn't have a sense of how our refueling process would work. And so we had a couple of maybe conceptual ideas of how we would get fuel into and out of our reactor core, but we had no conceptual design of a system or a robot that would do that. So when we did the first estimate of the MITRE, it came out to something that was just marginally more expensive than a 4-loop PWR, sort of a traditional light water reactor. And then if you march through our ARC-20 program, that was our DOE funded program, where we evolve the design, we add detail, we make sure that all the systems can as much as you can in a $4.9 million project. We make sure that a lot of the systems can interface, are likely to be able to interface if this were to proceed into detailed design. And we spent a lot of time, not in that program, but as ourselves in Boston Atomics, designing the robotic refueling machine that would do this, that would bring fuel blocks into the core. For the audience, our fuel blocks are, they're like a rectangular prism. They're maybe 30 centimeters square and 60 to 70 centimeters long, or a little bit smaller. And we got to bring in somewhere between 500 and 800 of these into the core and out of the core for our refueling process. And our core is, because it's horizontal, you're reaching in with like a 12-meter cantilever in some places to grab these fuel blocks. This is a very difficult machine design engineering problem. And so we hired a phenomenal engineer to work on this, Sam Quimby, who had experience in other sort of nuclear robotic machines. And he did a great job getting to a preconceptual version of what this machine would look like. But when he sketched out the whole process of how big the machine is, how it needs to reach into the core, where it's going to take the fuel afterwards, what the interim fuel storage looks like, then we did some analysis on how long does it need to be in interim fuel storage, and then where is it going to go in the plant after it's in interim fuel storage. And you do all this, and your building just grows. Like, the reality is, as you add detail in the design of your maintenance processes, the size of your structures grow. And so, whereas we were, if we were like, 1.2 to 1 on a large reactor cost comparison basis, in 2019, when we did the first estimate, we're somewhere closer to like 1.8 to 1 or 2 to 1 in today's basis. And that's just that's not just the refueling machine. That's just the example I'm getting. But you sort of propagate that through the hundreds of other systems you have in reactors, and you lose that initial conceptual advantage that you thought you had. And I think this is just the reality of detailed engineering, right? We're talking about incredibly complicated machines. And as you ask each of these disciplines to evolve their things towards a detailed performance, where it's going to be licensed through the regulator, it's going to be highly reliable, it's going to be easy to manufacture or construct. You put all those constraints on it, and you just get a system that's much different than your initially conceived system.
Yeah, it was interesting reading. I guess it's still preprint now, but the piece that you, James, and Garrett put out. And it's just interesting seeing the BWX 300 and its 2019 design basis and 2021 or 22, and just how much things had grown, how much the embedded vessel had grown in volume, all the systems that had to be added. I think that's probably pretty universal that you start off with some rose tinted glasses in terms of cost estimates, and then the detailed engineering always makes things complicated. Robbie, I wanted to chat with you a little bit because you have this experience with jet turbines and bringing these commercial products to market. There's a lot of advanced nuclear companies claiming that, with $100 million, they're going to have their first commercial unit up and going. It may not be full sized or whatever. But in terms of the games that you need to play, in terms of attracting capital, in terms of winning over investors in nuclear in particular, where you have such complexity and fine tuning, as you mentioned, in terms of getting to a final design, walk us through that a little bit. And again, touching on your experience with jet turbines.
I mean, I'll start with, at Boston Atomics, we tried to do an estimate of what it would take. What's the total capital required to get the first of a kind version of our reactor through detailed design and licensing? And we sort of always had this number, even from the very beginning, that was something on the order of $1 billion. And that was based on historical reactor designs done in the US and abroad, whether through national labs or through private companies. And late in 2023, we started comparing that number to other multidisciplinary design problems, right? So one interesting way to look at this is to say, well, what was the cost to design and engineer the Model 3 from Tesla? And it's, about $1 billion in design and engineering. And this is an electric car, right? It's less parts than an internal combustion engine car. And that's a lot of money for just the design and engineering. Now, there's a lot of prototyping along the way, but that's what it was. And you can also look at how much DOE money was appropriated to Westinghouse to do the design of the AP1000. And if you sum up the appropriations over 15 or 20 years, you get something close to $1.5 billion that was awarded to Westinghouse. And a similar number sort of is in the public data for what NuScale spent for the design of their reactor, their Voyager 12, or what was the US 600. And then you can go.
It's almost incredible that it's only $1 billion or $1.5 billion for AP1000 and $1 billion for a Tesla.
Yeah,
I
think that's the interesting thing to note there is, that was money spent up until 2012. And as I think has been discussed exhaustively on this podcast, is the design was not complete in 2012. And I've heard numbers that it was between 20 and 80% complete at the time. So there was a ton of engineering left to happen even after that $1.5 billion. And if you compare that number to like the Boeing 787, which at the time was the most efficient aircraft to be designed, and it was a $20 to $30 billion design and engineering effort to get there. And there's a lot of prototypes that happen along the way, but airplane prototypes are $300, $400 million efforts, not what you see in nuclear, where you have sort of $1 billion prototypes along the way. So, and there's some nuance here where aircraft are heavily manufactured products. And in heavily manufactured products, you're doing a lot of value engineering. You're doing a lot of manufacturing engineering. So you're spending a lot more time on the engineering itself. Whereas in a constructed product, maybe you're going to let your contractor sort of figure out on site a bit more than you would in a manufactured product. But in nuclear, we're sort of in this weird in-between place where you can't just let your contractors figure out everything on site. You need to have actually a lot of regulatory basis for how things are happening on site. So your design cost relative to a traditionally constructed product is going to be much higher. So if a traditional construction product is a design cost of 1% to 5%, you might be, significantly higher than that on a nuclear project.
Yeah, there's also another aspect that is interesting to comment there, and is the relation between the cost for engineering and development in a light water reactor like the AB1000 and an advanced reactor. Like, what's the difference? What we would expect to change from one to another. And whereas the AB1000, it's a more or less similar evolution to the previous concept before, that was the 4-loop PWR. When we think about some advanced reactors that are being proposed now, are not such a small step with respect to what was done in the previous version of whatever they're starting from. And you would argue, and many people argue, that there are simpler systems. Therefore, that makes the total design and development cost lower, and that might be true. But then there's a factor working in the opposite direction, that is, well, the little things that you are developing, how different they are from what was developed before. How much uncertainty does that add to your development process? And that's a factor that upgrades the difference. So we believe that it may be that in many advanced reactors, the development cost is actually higher than that 1 to 1.5 billion that we were speaking about before.
Yeah. And the other great example here is the Pratt & Whitney geared turbofan. So just to lean into my jet engine experience a bit. So geared turbofan, in jet engines, you actually want different parts of your engine spinning at different speeds, because you want your tip speeds to be not transonic, not above the speed of sound. And you have different diameters of things spinning in your turbine, and so that's different for different places. So the way this is kind of typically solved by folks at GE is a double spool or a twin spool engine. So you have your high pressure compressor, high pressure turbine on one spool that's rotating either inside or it's rotating outside of a second spool that's doing your low pressure compressor and your low pressure turbine. And this is letting things spin at different speeds. And all of that's and your low pressure turbine is also spinning your fan, the big fan you see at the front of your jet engine. But your fan is much larger diameter than anything that's happening in your engine. So ideally, you would even have a difference between what your low pressure turbine is spinning at and what your fan what your RPM of your fan itself. And so you're operating sort of suboptimally to accommodate these engineering constraints. And so starting in the early 90s, NASA was funding work at Pratt & Whitney to develop a gearbox that would let you sort of spin down the rate that your LPT is going to let your fan operate closer to its ideal fan speed. And NASA funded them for 10 years to do that. They tried a commercial product in the late 90s and they ended up not launching it. Then in 2006, they really doubled down and they say, we're going to do it. We're going to build the GTF, the Pratt & Whitney 1000, and it's going to be a geared turbofan. And the product finally launches in 2016, I think is the first delivered engine. So, right, that's 1993 is the first work on it. 2016 is when it's finally delivered. It was a $10 billion design and engineering effort. And you could say at the surface, all they did was add a gearbox to a jet engine, right? That would be a simple narrative to describe what happened there. But it's never that simple, right? Like, you're changing the speeds of things, which means you're going to change the aerodynamics of things. You're going to change the design loads of everything. So you're redesigning all of your parts. And in these highly multidisciplinary systems, one seemingly small effect has long downstream consequences. And that's the challenge of reactor design in general.
You have to pass everything through the structure of multidisciplinary teams, well hierarchically located in an organization that is very expensive to run. So even small changes are going to be expensive.
Do you feel like, coming from your respective fields, and in your case, Robbie, outside of nuclear, that there's something unique in terms of like a kind of design restlessness in nuclear? The sense that, things aren't good enough. We need to constantly be iterating. The ABWR had just been, the fastest constructed nuclear reactor, maybe in history, at least of a gigawatt scale reactor. And it was kind of like, we'll move on from there. I guess there were plans in the South Texas project to build a couple more, and maybe it's not fair to say it was just sort of passed over, but certainly in the last 10 or 15 years, where there's not really been much active nuclear construction going on, and a lot of hype and a lot of discussion. There's certainly this, what seems to me to be this kind of restlessness of like, well, what we have isn't good enough. We need to make massive step changes in terms of thermal efficiency or safety margins or things like that. Given the massive cost of R&D and the relative weakness of the Western nuclear industry, that seems odd to me.
Yeah, well, you say the massive cost of R&D. Remember, it's actually not that expensive to do a lot of conceptual design, right? If your goal, from a, say, national security perspective, is just to maintain a strong nuclear engineering workforce, and you just want to fund conceptual design and design evolutions over multiple years, but you never actually want to build a reactor, because building reactors are very expensive. They bankrupt companies, they bankrupt utilities, and so it's one way to just sort of fund academic and national lab work to continue to sort of meet this design restlessness that you're describing. And so if you're just trying to maintain a workforce, I think you could make an argument, and I don't know that anyone is actually thinking this way, but you could make an argument that if you're just trying to maintain a technical basis, and then the other thing I would say is, like, we are nuclear engineers. And so we are going to when we see problems as engineers, we're going to come at them from design solution standpoint, right? Like that is, we're going to see, oh, there was a problem with this reactor. How do I think about solving that problem? Well, I'm not an operations engineer. I'm not a supply chain engineer. I'm a nuclear engineer. And so I'm going to think about, like, well, what was the design problem that caused the thing that they observed? And the bulk of my energy I'm going to spend on, like, solving it from a nuclear engineering perspective. Now, if we were funding, if there was DOE research funding into supply chain engineering or operations engineering on these sorts of plants, you might see a different set of problems scoped out as solving the quote cost overrun problem in the industry.
So what was it like going to investors and saying, hey, we're going to need like at least $1 billion to get this concept through to potential commercial operation or demonstration?
Yeah. We actually got advice at one point that was like, stop saying it's going to be $1 billion in design and engineering to get to the first reactor. And it's because we really struggled. And it's not we should just be honest, it's not a compelling narrative to say that I don't need $1 billion today, but before I have a product that I can sell, I'm going to need to do $1 billion in design and engineering. And one of the other comparisons people make in nuclear is to SpaceX. And they say, look at how SpaceX took a highly multidisciplinary, very expensive process and were able to sort of slowly de-risk and build up through prototyping a product. But the first couple of Falcon 1 launches were something like $150 million or so. And so you're talking about they could fail three launches and then have a successful fourth launch, all for $150 million. And in nuclear, you're not even close to the design of a new reactor concept at $150 million, so, let alone having prototyped an integrated version of your reactor. And so we wanted to be honest about what we thought the total capital required was, because we didn't want to get into a situation where we had made some promise about how cheaply we could do it, and then we're accountable to that promise when we had known that this was a much more difficult process. And so we were sort of honest about needing at least $1 billion. And then, as I sort of alluded to, we realized late last year that the $1 billion was probably the floor, and that the ceiling was, obviously unbounded, but maybe close to between $5 and $10 billion in total design and engineering effort. And we think it's useful to talk about that point because we really like gas reactors. We think they fit an important niche in decarbonization industrial process heat. We think they have a great safety case. And if you want an advanced reactor industry and a high temperature gas reactor industry, we need to be honest about the cost of doing that so that we can create the programs, the R&D programs, the de-risking programs that can achieve that. And it doesn't help to sort of overpromise or maybe underestimate the design costs to get there. It's like, I think we have a simple understanding of solving problems, which is quantify the problem and then go solve it. And a proper quantification of the problem is that this is a multi-billion-dollar design and construction effort, and therefore we need to fund it as so if we want an advanced reactor industry.
And it's important to note here that the 1.2 to 1.8 times the cost of a light water reactor that you would theoretically get to, first of all, it's a cost model, and as such, It will probably be wrong, but it may be useful to quantify things. Second, this, even if it's totally true, it's 1.2 to 1.8 times or even 1.8 times a light water reactor. We believe, as we said before, that there are applications where it could fit and markets where it could fit. So this 1.8 is a general number that might not be the same for every place, for every project, for every subcontractor. And then there are applications like process heat where it may be worth it if you're going above 300C to build a plant that is 1.8 times more expensive. And that's how we initially got into high temperature gas reactors. It wasn't, let's deploy this technology instead of light water reactors. Let's find a technology that complements light water reactor for supplying process heat. Because for electricity, it will probably make the most sense to build light water reactors in almost most places, in almost every place actually as well. Doesn't mean that maybe a high temperature gas reactor at some point in the future may make more sense for some application and in some niche market or for some reason. So why an HTGR for process heat instead of a molten salt reactor, for instance? It was a high technology readiness level, and this connects to the cost of development that we were speaking about before, that if you're very different with respect to what has been deployed industrially before, then you have a bigger gap there. And that 1 billion to 5 to 10 billion in high temperature gas reactors, we don't know how much it would be in molten salt reactors, but we saw more of a gap there because we've seen less demonstrations. There's not the HTGR equivalent to molten salt reactors, and there's not force and brain, there's not AVR in Europe, there's not PBMR in South Africa, and so on and so forth. So we thought, well, the light water reactor is very well populated by teams that have a lot of expertise at designing light water reactors, like major US vendors, but also vendors in Eastern countries. However, we're not seeing that sort of innovation that improves high temperature gas reactors to a point where they could be competitive. And we believe that with our innovation, high temperature gas reactors can be competitive in those markets. So we have recently published a paper in IGAB that said that MITRE could probably be about 30% cheaper than other high temperature gas reactors. We don't know if, again, because it's a model, we don't know if it's 30, 20, 40, or 60. Like from the beginning of the project, we think that is in that range. And that makes it about 1.8 times the cost that theoretically, what you could get being reasonable with a light water reactor would be.
Yeah, I mean, in preparation for this, you guys had a table and some documents you shared with me about, and I found this to be useful as well. It's not the kind of be all and end all, but reactor years of operation certainly do give you a sense about technology readiness, troubleshooting that's occurred, optimization and capacity factors, and the water cooled fleet, 17,000 years or something like that. And gas reactors, like a lot of it's the advanced gas reactor fleet in the UK that when you actually parse it down to just the high temperature gas reactors, it don't look good. Like you have the Arbeit-Gemeinschaft Versuch reactor. I had to write it out in my notes because I love German. I love it. I can smash so many goddamn consonants together. But I mean, that ran for 22 years, not without problems, water, oil ingress, fuel failures. But like Fort St. Vrain, like 16% capacity factor. A lot of these, only operated for a couple of years commercially before being shut down. Like, is that not daunting to you? Like in terms of just the HTGR rather than just the gas?
Yeah, I mean, absolutely. I mean, and this is why, I want to throw a lot of credit towards the Kairos engineering team, because they've clearly laid out that the way to get to operational excellence is building expertise by doing a lot of technology demonstrations over time. And if you look at the history of even the PWR and BWR experience, there were a ton of small reactor demonstrations that were in the watt, kilowatt, megawatt size before we got to what we have today as sort of 1,000 megawatt light water reactors. And those processes themselves took a long time to get to commercial builds. And so the proper program to deploy an advanced reactor is something similar to what you can observe Kairos doing, which is doing a lot of these technology demonstrations, but it takes a long time and it's very expensive. Remember, Kairos has an engineering team of 400 or 500 engineers, which probably costs like, $100 million a year or so. Like I don't know, I've not seen their accounting books, but I can estimate that's what it's been. And they've been running for 4 years near that level. And the latest DOE press release on this, on Kairos, says that they'll do commercialization in the early 2030s. And so you're talking about, the Kairos reactor was conceived, the FHR was conceived in the early 2000s at Oak Ridge. It was an academic and university research project for 15 years. Then it became the commercial product for Kairos in 2016. And then 16 years of development after sort of starting the company to get to a commercial version of their reactor. And so that's like a very sober and like right approach. This is going to take a lot of capital. It's going to take a lot of engineering demonstrations over time, but that's how we're going to overcome those capacity factor problems that you point out at the HTGRs, right? Like if you just try to jump in and say, we've never built anything before, we're a new organization, and we're going to build a several hundred megawatt HTGR. I think it's not out of it's not crazy to expect that you're going to run into those capacity factor problems that you're expressing. Fort St. Vrain, there was only one reactor in the US before that was similar. And so it was sort of logical to say that this is not just a demonstration of one technology. Fort St. Vrain wasn't just an HTGR demonstration. It was a demonstration of new alloys. It was a demonstration of new fuel. It was a demonstration of new vessel types. It was a pre-stressed concrete vessel, new welding techniques, so there's when you do all of those things at once, you run into those capacity factor problems. And that's why you really want to have a program that can say, where we want to be in 15 years is this. And so we're going to have a focused and strategic vision over what we need to accomplish over those 15 years. And that's what we would hope for the advanced reactor industry.
It's really unfortunate for the HTGR community in the US that there have been so discontinuous efforts, in the sense that we had Pitch Bottom, then Fort St. Vrain, then few years of not much, then NGMP that started building up, but then it stopped, and now we have Advanced Reactor Demonstration Program. When we look at successful nuclear industries in other countries, what we see is continuity over time, continuity of effort and continuity of funding. And it's easy for these industries to justify many more resources deployed into advanced reactors, probably because of how the countries where these industries run are built and how projects are funded. But at the end of the day, if we aim to have a successful advanced reactor industry, we have to both commit and recognize. I mean, first recognize and then commit to these long development timelines and these very high capital needs. And we just have to look at the French sodium fast reactors, the Chinese high temperature gas reactors. All of these are multi-decade programs with non-stopping or almost non-stopping government support. And in today's dollars, you can be sure that they are all multi-billion programs. So it's going to be similar, right? Probably.
And I guess, yeah, it begs the question, I guess, within the U.S. where that patient capital comes from, particularly in a context of negative natural gas prices in the Permian, or $1 to $2 per million BTUs in other areas. What are your guys' thoughts in terms of where to attract that patient capital? Can that be venture? Does it have to be government? What are some examples internationally that might be applicable?
Yeah. This is a great question. And I would say, like, we will share our opinions here. And I would think that this is a useful conversation to have across the advanced reactor industry, because it's so fundamental to its vitality. Like the worst case scenario is that in 5 years, we've sort of spent the capital that's been deployed and we're sitting on half finished projects, right? So how do we make sure we can get these things through completion? And there's different ways of looking at this. One is, as Enrique alluded to, government-backed multi-decade vision projects. So that is the Soviet and then Russian commitment to the BN series lead-cooled fast reactors, the French multi-decade commitment to the sodium-cooled fast reactors, the China's current commitment to HTGRs. They started with their test reactor in the 90s, then they did the HTR PM, which is like a 200 megawatt, and then they're working on an HTR 600, which would be a 600 megawatt version of the reactor. So that's a clear R&D funded effort to get to what the commercial version of an HTGR would look like, the light water reactor competitive version. But that's a 30-year effort for them to think about that. And so that's like sort of option number one, is that we make Idaho National Lab what it was in the beginning, which is a reactor demonstration lab. It's building a lot of experiments it's building a lot of test reactors, and it's building experience and knowledge to get to commercial reactors in doing so. That's one. The second is sort of the philanthropic billionaire approach. We can give our ode to Mr. Bill Gates in this, right? Like he is committed to TerraPower and backing that project. I think that's a great way to get funding, where you have a billionaire who is committed and has the capital to sort of do this on their own, but it's not scalable, right? Like you're sort of subject to what this one individual wants to create. And then the last one is a successful light water reactor industry, right? Like if you look at innovation in other industries where you have a successful car market or a successful gas turbine market, you can fund R&D off of the free cash flow of a successful business. So if we can get to significant numbers of new light water reactor deployments in the US, whether they are AP1000s or ABWRs or BWX300s or SMR 300s, whatever they are, and if those can create healthy, financially healthy companies at GE, Westinghouse, Holtec, whoever it is, then those companies can fund the R&D sort of off balance sheet to get to the next evolution, right? When GE goes to do an evolution of their gas turbine, they pre-sell commitments to help fund some of it. They get, hey, this is what the product's going to look like. It's going to have these attributes, and they get commitments from airlines to buy that engine. And that helps give them the confidence that they can justify spending the capital to do the design. And I think in the industry today, we have such a disconnect between successful building and deployments that there's really nobody you can go to and sort of trust that if you buy this product at some set of metrics, you're going to get that product. But if we could get to the LWR industry to a healthy construction and deployment rate, then there's space to do advanced reactors in the wake of that.
Yeah, I was going to say that there's an important advantage of having a successful light water reactor industry for advanced reactors is that now we're showing so many projects and so many companies trying to develop their own advanced reactors, and there's no resources of every kind you can think of for bringing all those projects to reality, and that creates a lot of entropy, because those are teams, those are experts dedicated to a concept that will never come to reality, and some of them don't even have a chance. So the bigger question, looking at the big picture, would be how can we select those projects that really have a chance, that really are the best of their kind, that really have some reason to exist as they are, right? And maybe there's few molten salt reactor concepts that make sense in as projects. Maybe there's few HTGRs. We started MITRE because we thought is the HTGR concept that makes the most sense. Or in other words, the best way to build an HTGR would be MITRE. We don't have any doubt of that. And we think that similarly for other projects, if there was an entity capable of pointing at the projects that have the most sense and then canalizing resources towards them, so that the projects that don't have that much of a chance wouldn't get funded, and those projects that have a chance would get funded, that would improve a lot the chances of the overall industry. The good thing of a light water reactor industry being successful is that you have that expertise in nuclear engineering, that deep expertise in bringing a project to reality, that is going to be picking the advanced reactor concepts that make the most sense to complement their light water reactor portfolio. So it would be big vendors like Westinghouse or General Electric with lots of orders in their books for light water reactor that would say, and we're going to be developing as well this reactor and this reactor because they have the money to do so, instead of relying on government funds. There's another version of this that is not the light water reactor industry being successful, where we rely for advanced reactor mostly on government funds. But then it would equally be necessary to have the same type of expertise that we have in the first scenario on light water reactor vendors in the government for picking projects and for getting involved in projects very deeply to select which of them have a chance and invest very heavily and with a lot of continuity in those. So they will have better chances to get to fruition.
Yeah, I mean, I guess that one model is, and this is kind of the dynamic free market capitalist model where you have the market choose the winners and losers. But, certainly in the last 10, 15 years, we've just seen a plethora of SMR concept companies spring up. And as you're saying, it's a pretty disorganized approach. The other side would be some degree of central planning, whether that's government or just, a large company, a large healthy company like GE or Westinghouse potentially having, I I guess, better tools with which to decide on, which concepts are more likely to be deployed. I think it was interesting seeing Great British Nuclear narrowing down their SMR technology choices and basically limiting everything that was in the light water reactor. I'm not sure if that came as a shock to some, but it certainly was something that I noticed. And when you're looking and starting to look, more at the economics and dollar and cents and likelihood of good operations in a project, that just makes sense. I think that brings us back a little bit though to your cost estimation tool as well, like having trusted, standardized tools that can be used to make these kind of assessments seem really important in this context.
Yeah, absolutely. And making those sorts of decisions. And one of the things that comes up when you do that for advanced reactors is, and one of the novel aspects of the tool is that it sort of assumes a base number of systems that you're going to have in your plant. And if you come at your advanced reactor concept cost estimate from you only need to estimate the cost of these, 10 systems because that's all my advanced reactor has, well, then your cost estimate is going to look great. But if you start to back out all of the maybe regulatory requirements or just systems engineering type requirements that you need in your plant, and you all of a sudden need HVAC and safety HVAC and redundancy in some of your wiring and different rooms for those things to happen, and so that you have adequate fire protection, you start applying all these other constraints. That first cost estimate that you had, was low because you underestimated the number of systems. So one of the things I think, I can't speak to the British government, but I know some utilities who have used the cost tool I developed. When they approach a vendor and they say, "Give me the size or some metric of this system," they don't know because their design concept is so early. And it's actually a good tool for evaluating where somebody is in their design processes. Can you actually tell me what your flow rate through your helium purification system is, or the flow rate through your chemical and volume control system is, or can you give me some sense of the necessary capacity for your service air, water, and steam? And if you can't provide those things and you're just thinking you don't need them, then it's clear that your design is at a very preconceptual phase. And I think as you start to get the experts in the room to analyze these things and make estimates of what should come next, you kind of approach maybe the next round of deployments really should be light water reactors because of just where they are in their development.
I don't know if this has changed in the last 1 month or two, but at least until April, that I went to a conference where they presented, there was still ongoing a program in the UK for developing high temperature gas reactors in collaboration together with Japan. So it being true that they ruled out most advanced reactor concept, they picked one. And this is exactly what I was speaking about. Like, it doesn't need to be, we rule out all the advanced reactors because all of them don't make sense. Let's concentrate on SMRs or on big LWRs and so on. Let's pick the few things that have a chance of being cost competitive at some market that is also big enough to justify the investment, and let's carry on with that. The UK, to my knowledge, they opened a program a few years ago for developing HTGRs for the country, and there were 4 consortia that were selected. One of them was led by the National Research Laboratory from the UK, but there were also another set of vendors, private companies international, that won in collaboration with UK companies these pre-feasibility studies for technology selection. And I don't know if now they have narrowed it down to less concepts, but until at least recently they have some program for developing high temperature gas reactors.
So maybe we'll sort of wrap it up shortly here, but wanted to get a sense from you guys. You're incubating MITRE, but what's new? What are you guys putting your efforts into now?
Yeah, that's a great segue for the rollout. So we are incubating MITRE as sort of still allowing for research collaborations on that front, right? So if you're a university or national lab and you want to work on an advanced reactor, we'd be happy to collaborate with folks in that space. But we think that the next big move, or I should say, I think that the next big move for the nuclear industry in the US is we need to deploy more light water reactors. And that can come as, power up rates of existing reactors and as deployments of AP1000s or ABWRs. And So the question is, how do we get there? Like, how do we make that happen? And I think there's still a lot of questions there. There's still a huge gap. I think there's a missing business model that exists to get those things deployed. In the US, there's a missing group to both manage the project well, absorb the risk, and capture the value from deploying that. In the US right now, we have phenomenal tax credit support for deployments of nuclear reactors. 30 to 50% of your total capital costs can be basically refunded to you through an investment tax credit, depending on how much domestic content you have in the plant. And that's like how much of the steel and rebar came from the US and how many of the manufactured products came from the US. And if you're in an energy community, which is almost all of the US is an energy community. And so there's, and if you don't want that, you can get a production tax credit. And then we have a lot of states that are willing to pay above market for clean, firm power. And a lot of customers. There's a lot of data centers and even other folks that are trying to get clean, firm power on their balance sheet, willing to pay above market for nuclear. And so that I think we're in a place, in a moment that I would be, disheartened to see if we missed it on deploying new light water reactors in the U.S. right now. And so, in that vein, we started working with another group called Alva Energy to sort of expand the deployment of light water reactors in the U.S. And I will say we'll give more clarity on what that looks like in the coming months. But the goal is to get, whether they're ABWRs or AP1000s, sort of under construction in the U.S.
From your lips to God's ears. Any closing thoughts, guys, before we sign off?
No, this has been great. I really appreciate it. I guess my closing thought will be that one of the things I've valued a lot about Decouple is that you've tried to have these heterodox, nuanced conversations about, and I think why we were comfortable coming on here and sharing what we think it takes to get an advanced reactor industry really rolling. It's because we knew that your audience is eager to hear that sort of thing. They're like willing to accept that it's maybe going to be more complicated than some are saying. That doesn't mean it's not worth doing. But let's be honest about the problems and challenges of getting this underway. And so I would say shout out to you and the Decouple team for this nuanced approach to all things nuclear and decarbonization. Cheering y'all on.
Yeah, and I also wanted to add, thank you for having us here as well. This has been great. I listen to many of your podcasts. I think you bring up a lot of topics that are not familiar to most people in a really relatable and easy to understand way. And it's always interesting to listen to the guests you bring in. Last note on Boston Atomics, something we didn't mention we're incubating internally the MITRE concept, but we're also providing consulting and R&D services on technology development aspects that are not directly related to the MITRE to our reactors, or to other HTGRs or to other nuclear technology.
Okay, guys. Great chatting today. Look forward to more of the same.
Thanks, Chris.
Thank you, Chris.